Hello. We talked in a previous video about translation turning messenger RNA into polypeptides, which are basically composed of amino acids. And I want to look into what the baseline structure of an amino acid is and what the different amino acids are, because those are the building blocks, the fundamental building blocks of proteins. So amino acid is kind of in the name. So this left-hand side with the nitrogen group, the NH3, is an amine. And on the right-hand side is a carboxylic acid, so amino acid. And there's an alpha carbon here, which is where all of our side groups, or side chains, bind. And these different side chains are what give each amino acid its unique chemical property. And each side chain is what creates the name for the molecule, and we have 20 different amino acid side chains. And each one has been assigned a letter in the alphabet, a 3-digit abbreviation, and a name. And I'm going to go through those here in what I'm going to call our amino acid ABCs. So the first one is ALA, or alanine. And all that we're doing for this one is we're adding a methyl group onto that alpha carbon. And this is the first in our class of nonpolar hydrophobic side chains. So what that means is that it's not going to like to be around water. Instead, it's going to hide on the inside of any protein that it builds in. So inside of proteins. There's no B in the alphabet for amino acids. C is cysteine, C-Y-S, cysteine. And cysteine is an interesting one. It has this intermediate carbon out to a thiol group. And in a given protein, we often see that these will stick out into a loop here. And when they're in close proximity like this, these hydrogens will actually bind to each other, and there's going to be a bond that forms between these two sulfurs, and that's known as a disulfide bridge. And it's a structure within polypeptides, and it helps to bring those closer together. And it's a covalent linkage, which is different than any sort of ionic or hydrogen bonding that you're going to see. So this is a very strong bond that's going to keep that in a tight loop. D is our aspartate, ASP, aspartate. This also is known as aspartic acid, and that just depends on the way that you write the molecule. So there's going to be one carbon intermediate out to a carboxylic acid. And because I've drawn this carboxylic acid with a negative charge rather than with an H, we're calling it aspartate instead of aspartic acid. So this is a charged side group. It's a charged side group, which also makes it hydrophilic. And we see that it's going to want to interact with water. So we'll see it often on the outsides of proteins and playing a larger part in reactions. E is its counterpart, glutamate. And it looks just like aspartate, except for it has an extra intermediate carbon, so 1, 2, out to a carboxylic acid. And we can also call this glutamic acid if we were to turn that negative charge into just a hydrogen attached to that. It has similar chemical properties. The way that I remember the difference between aspartate and glutamate is that there's one as and two glutes. Just a happy little mnemonic that will help you remember that. So F is phenylalanine, which can get confusing. But the nice part about phenylalanine is that the structure is in the name. So we remember that alanine is just a methyl group sticking out. And for those of you who have taken any organic chemistry, you'll remember that a phenyl is just a benzene ring or an aromatic ring sticking out here. And so that's what this looks like. And phenylalanine is unique because of its aromatic structure. And an enzyme known as trypsin, which is something that a lot of biochemists like to talk about, is an enzyme that will come on a polypeptide, and after particular residues, it will cleave the polypeptide into two smaller units. And so after an F is one such place where trypsin will cleave the polypeptide into two smaller polypeptides. G is our simplest amino acid, and that's known as glycine. And glycine's side chain is actually just a hydrogen. And if we're paying attention, you also notice that there's a hydrogen behind each of our side chains as well. And it's always that the R group that we're talking about comes out in the front, and that hydrogen hides in the back, and we call that the L configuration. And all of the amino acids in our body are naturally in the L configuration. It's just the easiest way for us to use. Glycine is the smallest amino acid, and it is very prolific and useful around the body. H is histidine. And histidine is one that's very reactive, so we see it in a lot of enzymatic different reactions, and so it's a very important one to probably just memorize. And the reason that this one is so useful is because it's able to shuttle around these proteins. So this amino group can grab proteins, and this one can lose proteins happily. And so we see a lot of shuttling reactions with histidine, and this can be a charged molecule under different circumstances, so it's pretty hydrophilic. The next one is isoleucine. Isoleucine. Isoleucine looks like a chair, in my opinion. It has 4 carbons, and this is another one of Alanine where it's nonpolar and hydrophobic. So it's going to hide on the inside of molecules of proteins. There's no J in the amino alphabet. It is counterintuitively known as lysine. And it's another one of those positively charged ones. And so lysine has 4 intermediate carbons, 3, 4. We've drawn them in. And it ends in an amino group that can become charged if this set of lone pairs grabs a hydrogen. So in that circumstance, it's charged. So that's another one where it's hydrophilic, or it's going to be on the outside facing the environment. L is leucine. That one looks a lot like isoleucine, except for it's just 1 carbon removed. So where isoleucine has the carbon there, the extra methyl group there, leucine has it moved out to the end, and it's like alanine, where it's hydrophilic, and it's going to hide on the inside of molecules, and it's nonpolar. The next one is methionine. And like phenylalanine, methionine has its structure, built its name. So we're going to come out with these 2 intermediate carbons going down to a sulfur and another methyl group. This sulfur group is a thiol, and this ending is a methyl. So we get the name methionine, and that one just has some interesting chemical properties, but it's not an overly common amino acid. We find it a lot around codons, so that's an interesting way for things to recognize that there's the start of a protein. N is asparagine. And it starts off with this as, which is like, we can remember that we're talking about something that looks a little bit like aspartic acid or asparagine, but it has this amino group on the end. So we're going to want this double bonded O for an amino group at the end instead of an acid at the end. And then there's no O, it looks too much like an oxygen. P is for Prolene, not to be confused with phenylalanine because that one starts with F in its abbreviation. And Prolene is a wacky one because instead of having just a side chain floating around, it actually links itself back up to this amino group into a 5-member ring. And this is one of those non-polar hydrophobic molecules, but we often find it kind of in loop structures on the ends of proteins, and that's because it doesn't like to interact with the other amino acids as much as other amino acids like to interact with themselves. So it kind of tends to be a loner hanging out at the end of loops. Q is glutamine. That's an N. And just like glutamic acid is the counterpart to aspartic acid, glutamine is the counterpart to asparagine. And we can think about that. Remember, there's one as and two glutes, so one carbon, two carbons coming out to that terminating amine group, that NH2. I've drawn that poorly. NH2, that terminating group down there. Now this one is polar hydrophilic. It likes to interact with its surroundings. The next one here, R, is known as arginine. And this is one of those positively charged amino acid groups. So it has 3 intermediate carbons, 1, 2, 3, goes down to an amine, which comes double bonded out to another nitrogen group and ending in an amine. And this one acts a little bit like histidine, where because of its double amine groups, its kind of its chemical structure, it allows it to ferry these hydrogens around a little bit. It can play with those, and so this is often a positively charged molecule, very hydrophilic and likes to participate in reactions. Chymotrypsin, like trypsin, cleaves polypeptides into smaller parts after residues, and chymotrypsin does this after positively charged residues, so arginine and lysine, and trypsin tends to do it after aromatic residues. So the next one that we can talk about is serine. And serine looks like cysteine, except it has an alcohol instead of a thiol at the end. And so this one has similar chemical properties. It's very hydrophilic and it likes to hang out near water. T for threonine. And that one looks very much similar to our serine molecule, except for it has this extra methyl group hanging off the end. So it's not quite as polar and hydrophilic. It's just kind of a neutral hanging out. It likes to just be around. The next one is valine. And valine is an easy one to remember just because it kind of looks like a V hanging off of our alpha carbon. And this is another one of those non-polar hydrophobic molecules, so it's going to be found on the inside of proteins. W is known as tryptophan. So not only does it have a very long name, but it's also kind of a complicated looking molecule. I'm going to take my time when I'm drawing it out. So there's an intermediate carbon going to a double bond, which heads to a nitrogen, and this creates a 5-membered ring, which also attaches to an aromatic ring. So this is one that trypsin cleaves after because of that aromatic structure. The next one that we have is tyrosine, or TYR. And tyrosine looks a lot like phenylalanine, except it has a methyl group sticking off the end. Now there's no Z, so we've reached the end of our amino acid. I think that was a pretty wild ride. You guys have gotten a lot of, oh, I'm sorry, this has an alcohol hanging off the end. I'm glad I waited. Thanks for watching. Have a good one. Adios.